So, hi everyone. It will be a very long and talk with a lot of information. I put a lot of links in the slides, so the slides will be available after the event. So feel free to download it and check the links. It was intentionally done this way, so you to have an option to track interesting links on your own. I will not explain every slide, and actually my goals, as I mentioned here, is not to describe everything in the field. It's not possible, but I'd like to highlight some important chips and important things that happen in the field right now. I do not want to compare technical characteristics because it doesn't make sense without your particular tasks, but I use some numbers in different slides just to have some reference points and to make your life easier if you want to start comparing different solutions for your particular needs. And I also will not recommend what to use. Again, it heavily depends on what exactly you do, and there are no general solutions that's useful for every case, so that's not an option. My goal here is to give you a broad picture, broad overview of what's happening in this exciting field. And I believe hardware field and hardware for deep learning is very exciting because right now is golden era for hardware. We have a huge boom on different new solutions, and it's some of them are really beautiful, and I always love to dig deeper to the base levels of everything I try to study. I started programming with machine codes, not even assembler, so I loved always to understand how things are happening on the lowest possible level, and hardware is very important level to understand how your software solutions work. And again, in deep learning right now, in hardware, it's golden era. We haven't seen such Cambrian explosion for a long time, and it's good time to be here and good time to dive into different hardware things. So let's start. Obviously, we have several choices to use for deep learning. It's impossible to avoid CPUs. Every computer has CPU, and some of your work is definitely done on CPUs. And with CPUs, we actually reach some kind of limits. Scaling doesn't work so well. It worked previous decades. Much of our computers is still x86 architecture, but for those who use Macs and some other, it's not a single choice, not the only choice for now. But anyway, typical processor right now is multi-core processor. It's very hard to find a single core processor right now, so almost all programming right now requires some understanding of distributed system, parallel programming, and so on. And typical system has from 2 to maybe 10 or 12 cores right now. Some advanced expensive chips have up to, for example, 18 cores, in case of AMD up to 64 cores. But generally, it's the upper limit, and for x86 architecture, it's hard to, or impossible to find anything larger. For servers, you have a bit higher or average, but it's still limited by, for example, 64 cores and twice more threads, and that's it. And you have some other additional options. CPUs are important because, again, it's impossible to avoid them, and many companies have some clusters, a lot of service with CPUs, and you have to use them efficiently. And there are a lot of optimized libraries. There are special instructions in modern processors to use in deep learning, in machine learning, in different vectorized calculations. You definitely heard about AVX instructions. AVX 512 is the latest, largest set of instructions suitable for deep learning. It's not the only one. There are some additions like VNNI, DL Boost in Intel. So modern software and model libraries, especially from Intel, use these instructions, and these instructions add a lot to your performance. And if you dive to this level in assembler, you can optimize your code and performance significantly. And in most cases, you don't have to optimize because there are a lot of already optimized libraries from Intel. For example, you have BigDL, you have PlateML, you have OpenVINO, you have a special Python distribution from Intel. So don't limit yourself by default Python distributions. Use these optimized ones because it can give you a significant boost. Actually, in Conda, you already use something like this, but anyway, it's almost every time you have options to make your code faster without changing anything except the distribution and libraries. Interesting thing is I recommend to watch for is MLIR. It's a technology developed by the same person, Chris Lattner, who developed LLVM, and it pretends to be a more general intermediate representation for not only for compiling typical programs, but for machine learning as well. Just keep track on this project. It's interesting. There is an open group you can join to discuss in design decisions with Chris Lattner and other people. So you can find it on the internet, join and contribute to worldwide research. Right now, it's possible. And with CPUs, there are many different important dimensions. Just to mention a few, I will not dive into each of one, just to highlight that performance is not the single only important parameter. There are many, many other important things to think of. Yeah, so x86 is the most common architecture, not the only one, as I mentioned. ARM flourished last several years, and we have a lot of different ARM processors. Modern MacBooks are pretty cool, and their performance is really great, even without GPUs right now. And we have a lot of server-side ARM processors. We have many ARM processors in your mobile phones. So ARM is a great architecture. It's heavily used right now. If you want to spend your time in low-level programming, ARM is definitely one of real choices right now. It's worth spending time to learn ARM assembler if you want to. It definitely makes sense. Last several years, there was a NVIDIA tried to buy ARM. It wasn't allowed to do so. So ARM still a separate company, but it was a huge event, actually. We understood that ARM is definitely a big player. So if NVIDIA wanted to have ARM under its umbrella, so it makes a lot of sense. And there are other interesting processors. IBM Power, I like it. For a long time, it was the only processor that had NVLink directly on the processor side. So the CPU could use NVLink to send data to the GPU with much higher bandwidth than PCI Express. It was really cool, but since Power 10 architecture, it's not longer the case. With PCI Generation 5, IBM said that there are no more sense to use NVLink. I actually don't believe in it, but NVLink, I think, still have much larger bandwidth. But again, PCI Express Generation 5 is faster than Generation 3 we had previous years and 4. So, okay. But anyway, it's interesting processor. It's very powerful, but it's hard to use it, hard to get it. But if you had a choice and have an option to access such hardware, it's very interesting. And another interesting thing is RISC-V. It's an open source architecture. It's if you know Dave Patterson, who's the author of one of the main computer architecture books, and he also significantly contributed to Google TPU version 1 and others as well. Dave one of creators of RISC-V architecture, and there are a lot of movement in this field right now. There are several very multi-core processors. You probably heard of Esperanto Technologies company that produce a chip with more than 1,000 cores. That's very interesting. It's interesting how to program such chips. You probably need some very special language and software system, maybe something like Erlang or ecosystem would fit well into such hardware. I think it's very interesting field on its own, and multi-core processor with 4,000 cores is very interesting as well. Waiting to have such chips available to ordinary use. Yeah, so that's basically it with CPUs. I just wanted to highlight that Intel and x86 architecture is not the single only option right now. There are many other, and they are constantly developing. Obviously, the next big thing is GPU, and right now the most of deep learning calculations performed by GPUs. GPUs actually is the thing that made deep learning affordable, and with GPUs for a very long time already, you can train big models that you cannot train with CPUs. It's much cheaper, it's much more energy efficient. You can get your models in much better time. And again, there are a lot of important dimensions here as well. Peak performance is not the single only important dimension. It could be not important at all at some cases. Precision is important. For a long time, deep learning was mostly concentrated on FP32, a single precision floating point. But it's not longer the case as deep learning moves or shifts towards lower precision training, for example, FP16 or brain float or mixed precision training and so on. And it's still moving into even lower precisions like FP8 or even integer precisions. Integer mostly used for inference, but there are some research to try training in with these lower precision and integer modes. It's interesting on its own. And there are some special formats like BrainFloat, developed originally by Google Brain team. It's a special version of FP16 with the dynamic range of FP32. And there are other interesting things like TF32 and so on and so on. I even have an article on these different formats, so feel free to track it and read if you're interested in it. There are many caveats with precision because gaming cards are usually limited in different aspects, and only professional cards provide you with really good performance. But again, it's a separate topic. If you want to dive, just track this link. Important thing with GPUs is that there is a good model that explains performance. It's called roofline performance model, again by Dave Patterson, by the way. It means that there are actually two limits. One, the upper limits is computational roof. It means that your computations are limited by your computational hardware. Computational hardware is loaded at its fullest possible mode, and it constantly crunch numbers, and this is the limit. Peak performance is important in this region. But there is another region, it's those I/O bandwidth roof. In many cases, your computations are limited by the speed with which you transfer data to GPU to be processed. And in many real-world applications, you are far from peak performance for different reasons. And it's important to understand which of these limits exactly the case for your particular case. Maybe you don't want a faster GPU, I mean more performant with more cores. Maybe you need a GPU with better memory bandwidth, and it will solve your problem, not the fastest one. So it's a bit tricky to measure all these things, but if you can do it, it's worth doing it, because with this knowledge you can better optimize your particular calculations and invest in hardware wisely. There are a lot of NVIDIA architectures. It changes constantly, and right now I think the most modern one is Hopper, but you can correct me if I'm wrong. Almost any new architecture brings something new and very interesting. With previous architectures, we have sparse computations that are really important for many deep learning workloads. With the latest architecture, we have several other interesting things like transformer engine or instructions for dynamic programming, or even confidential computing. That's pretty interesting on its own, and many other things. Just some numbers for your reference if you want later to compare between different solutions. Right now, it makes no sense to just look at these numbers. But what I wanted to say is that NVIDIA is not the only option here as well. It's still the most affordable and most usable option, mostly because NVIDIA has great support in software, and Intel and AMD have a lot of problems with community support, but they have hardware, and sometimes it's pretty good and interesting. Intel have their own GPUs. It's not the fastest one GPUs, but it's still interesting on their own. And AMD has a really great hardware with their pretty awesome characteristics. But again, the main question is how is it supported in TensorFlow, PyTorch, and other framework you use. AMD has their own solution called ROCm, but there are still many open questions of how is it applicable in each particular case. I think there are a lot of caveats there. But again, hardware is really interesting. This is a pretty old slide. I made it manually by gathering all the characteristics. It was used mostly to highlight the trend, kind of exponential or something like this. And here you see only mostly gaming cards, and I stopped updating this graph because actually it makes no sense. There are many different performances you can measure. Here I highlighted FP32 without tensor cores. With tensor cores is completely different story, and with FP16 is another different story. With int8 is again another story. So right now it makes no sense to use these graphs, but anyway, it highlights some trends and they're still important. For example, for recent NVIDIA and AMD GPUs, the points would be much higher, and the trend still continues, and we have more and more powerful hardware each year. That's great. Single GPU systems is not their single and not the only choice for a long time. You have many multi-GPU systems, and you have actually distributed learning. It's already a commodity for several years. There are many different frameworks to use distributed learning. The only problem is distributed training is actually still sublinear. You invest some money in your hardware, but your benefits beyond the linear trend. But again, it's better than nothing, and different solutions have different trends in different scaling, so that's good. And basically, AI became the data center level AI. We have different pods, super pods by NVIDIA, by Google, by other companies. Right now, data center level supercomputers for AI, for deep learning, is not necessarily commodity, but pretty common thing if you can afford them. So is everything okay with deep learning now or not? Obviously not. We still have many problems, and one of the main problems is energy efficiency. And there are several solutions to solve these issues. FPGAs. FPGAs is a special chips, programmable chips that you can programmable on the hardware level, kind of. You can reprogram chip to implement your own scheme, your own custom chip, and use it for different things. And it will be much faster than if you program a universal chip just with programming language. So here, FPGAs are a great choice if you can afford them. It's pretty costly and pretty expensive to use them. And another big problem is learning curve is very steep. It's hard to dive into this field because it takes pretty decent expertise, and it's much harder than to dive in current machine learning or in software engineering. But there are different solutions, and interesting, there were two big players in this field, Altera and Xilinx, both acquired first by Intel, second by AMD. So right now there are no big separate vendors of FPGA. Both are under umbrella of large CPU, large processor companies. And FPGAs are used and still used in production in many cases. I highlighted some of them. The most affordable one is AWS has a separate special type of instance called F1 instance. With FPGA, you can program your own special hardware and use in Amazon Cloud if you want to. And actually, FPGAs are pretty complex things that there are not only special logic gates that you can program, there are actually special modules for called AI engines or DSP engines or some other types of engines. And you don't have to implement every possible hardware solution from the scratch. There are separate libraries of IP, there are separate special modules you can use for your special calculation. So it's interesting field again on its own. But that's not the mainstream in deep learning. Typically, only large companies can afford it, and fintech is heavily used it. But for deep learning, it's kind of not a very common thing. ASIC is a very common thing right now. ASIC is a application-specific integral circuit. Actually, if you tracked what happened in Bitcoin several years ago, Bitcoin followed the same track. Everyone started mining on CPUs, then they switched to GPUs, then on FPGAs, then finally different companies start producing special chips just for mining. That's ASICs. The same with deep learning right now. Almost every company has its own special processor, tensor processor or neural processor or something like this. And it makes sense. AlphaZero was trained several times on different hardware, and early versions was trained on CPUs and GPUs, and they consumed some amount of power, pretty big. And later versions, which are more powerful and won over previous versions, took much less power to train these models because they used newer hardware. I think AlphaGo Lee was trained on TPU version 1, and later AlphaGos were trained on later TPUs, version 2 or 3 maybe, I'm not sure. Google right now has 3 different versions of their TPUs available in the cloud. TPU version 2, version 3, and last year they announced version 4. With every subsequent version, you have much more better performance and typically better energy efficiency. It's an interesting architecture. If you want to dive into architecture, feel free to follow the links. I have an article in Medium that explains much deeper most of ASIC architectures I will show here. Again, these ASICs are not a standalone processor. They're actually standalone processor, but the main mode of using them is multi-chip configurations, and Google has pods and superpods with these chips. It's actually very powerful supercomputers. Here is a TPU version 3 pod, I think with 1000 chips. The TPU version 4 has an option to join 4000 chips, and we'll see what we'll have with version 5. Google TPU is the most affordable solution. You can rent it in the cloud and use it, and Google has good software support. You can use TPU in TensorFlow, in JAX, in PyTorch, almost any modern deep learning framework supported. But it's not the only choice. Intel acquired Habana, is interesting startup. I think Israeli one, but I'm not sure. And Habana has two different chips, and that's pretty common distinction. You have a separate chip for training and separate chip for inference. For inference, you need much lower performance, but you typically need better latency. And there are two chips. Actually, it's second generation chips. They were announced, I think, last year. And right now you have Gaudi 2 and Greco. And Gaudi 2 actually outperforms NVIDIA A100 by one of the metrics at least. So it's interesting hardware on its own. Again, it's interesting to read about the architecture and to understand how it works. And Habana is available on AWS as well, so you can start using it and trying which one is better for your particular case. GraphCore is another interesting UK-based company. They produce their own IPU. Again, a special type of processor. It's pretty big, pretty interesting processor. Again, its architecture is a separate interesting thing. Just dive into it and try to understand how is it different from any other solution. But it's interesting. It has own software stack to compile programs to use on IPU. But they have some kind of adapters or some versions of TensorFlow to use with this processor. But I didn't try it yet. But it's an interesting option. And IPU is kind of available in the cloud. Again, I didn't try yet, but looks like you can use IPUs and you can buy this hardware. It's expensive, but comparing to NVIDIA, it's, I think, in similar range. So it's an affordable option.
4,000 per week.
Yeah. Interesting. Another very interesting solution is Cerebras. You probably heard of this, the largest world GPU. It's actually a wafer scale GPU, not GPU, it's chip. It's a big chip consisting of actually, it's a second generation of this chip. It consists of more than 800,000 cores. It's a super massively parallel architecture, and Cerebras built their own complete solution. You can rent or buy. I think it's very costly, maybe $1 million, something like this. But it's very interesting hardware. If you can get access to it, it's interesting to dive into it and to try to program. It's completely different experience. It should be completely different experience. Amazon has their own chips, both for inference and training. Huawei has their own chips. Bitmain, interesting, that's the company that started in Bitcoin, switched into deep learning and produced their own chips. Alibaba has their own chips. Baidu, Grok is an interesting solution founded by the person who co-founded, who actually was behind the first Google TPU as well. And Grok seems to be designed for ultra-low latencies, and typical problem for inference is to have low inference on small batches, and Grok kind of tries to solve this particular problem. Again, it's very interesting solution, and again, there are many others. I highlighted some of them. In half a year, we'll have more. So just keep track on this field, and it's a very exciting field, and you probably have much more options soon just to train your models and to use in inference. You already have several options you can choose right now. It's worth trying if you want to heavily optimize on particular hardware and for cost, for example. Yeah, and the problem with ASICs is in it's very diverse field, and it's hard to compare different solutions, and it's impossible to compare by numbers, because these numbers typically do not mean anything important for you. You need kind of benchmark, and it's great that we finally have some common benchmark. It's called MLPerf, and in MLPerf you can compare different solutions on typical problems like ResNet training or transformer training and something like this. Yeah, and pretty separate thing is mobile and the edge. Again, you have a great variety of different chips. Almost any company has its own chip for mobile. It's hard to find any company who produces mobile phones and has no special chip for optimizing AI in any way. There are interesting solutions for other edge things like robots or devices, great Jetson Nano and other Jetsons as well. Interesting solution from Intel. Intel acquired another company called Movidius, and you can use this USB stick to upload your model, and special processor on this device will calculate your model weights and all the computations, and you can plug it into Raspberry Pi, for example, and have Raspberry Pi with pretty decent AI capabilities. And it's interesting that Google have its own version of Edge TPU. It's not that large TPU that you have in the cloud. It's a pretty small one, but it's affordable. Again, it can be used with USB device. Can plug it to Raspberry Pi and have face recognition on this small and cheap computer. That's great. Right now, you can build very different solutions pretty easily and with common software like TensorFlow. So that's great. And again, there are many other solutions. I cannot highlight everyone, just to give you understanding that the field is very diverse as well. So, is that the whole story or not? Obviously not. Some problems still exist, and one of the problems is still energy efficiency. We have a brain that consumes maybe 10 watts, depending on the brain and particular organism, and it's hardly comparable to all the hardware solutions we have. Current architectures are very specialized on matrix computations, but we want to have some more brain-like computations, and of course there are special chips for that. I took this slide from some of Intel presentation. I like it. Let's compare Parrot with Drone. Parrot have much smaller brain that consumes much lower power, and it can do great and amazing things that our drones still cannot do. How to fill this gap between biology and artificial systems? There are neuromorphic chips. You probably heard of them. If not, start looking at this field. It's very exciting. Neuromorphic chips are special chips that are designed to mimic brain-like computations. There are very different chips and very different technologies, but the idea is that current deep learning is mostly about multiplying dense or even sparse matrices, but it's still far from biology, and biology uses spiking neural networks, asynchronous computations, and biology hardware is very different. Many companies and many research institutions try to implement something like this. And again, this is a slide from one of the Intel's presentation. Important thing is that this new neuromorphic hardware is typically spiking hardware, and it's heavily parallel as well. And what's important, it's asynchronous. There are no single timing device. There are no single schedule upon which every computing devices calculate something. There are some cores, some units that got excited in different times and they communicate to each other, and that's completely different story. And one of the most famous chip is IBM True North. I think it's older than 10 years, maybe a bit less. It's pretty old chip, but very interesting. IBM used it in different research, and the chip consumes 70 milliwatts. It's really great comparing to hundreds of watts typical GPU or TPU consumes. And these processors are usually compared by number of neurons, synapses, and something like this. But again, implementations could be very different behind this neuromorphic hardware. IBM tried to convert some of the typical common neural deep learning networks into these spiking neural networks. Their approach was pretty successful. These spiking neural networks on this hardware works pretty well. You can achieve meaningful results with much less amount of power, and that's interesting. Right now, it's mostly research direction, not a production one, so it makes almost no sense to use these chips for your current deep learning models. It's a completely different story. It's for those who want to contribute to some new field and design some new types of neural networks and maybe new products with it. But it's interesting, and this is where the field is going, at least one of the directions. Intel has its own chip. It was called Loihi. That was the first version of the chip, and Intel assembled several systems of several multi-chip configurations. The largest one, I think, was this one with 768 chips and actually 100 million neurons. That's pretty decent amount. And last year, Intel announced the second version of their chip, Intel Loihi 2. Again, there are differences between Loihi 1 and Loihi 2. We have no time to dive deeper into it. Just follow the links if you are interested. The chip is interesting. Architecture is very interesting. It's completely different from our common hardware. Intel started building some system on a chip, one single chip system for research or several chip systems for research, but maybe for some more heavy uses. Intel also developed and made open their own new framework called Lava. It's framework for neuromorphic computations, and actually Intel had before another framework. They called it NX SDK. NX looked more like Keras or something like this, and was heavily linked to Loihi 1, and that's it. And Lava is a bit different thing. Intel pretend to be for Lava to be kind of hardware agnostic and can use CPUs, GPUs, neuromorphic hardware. It's built in completely different ways. If you know distributed and parallel programming, you probably heard of CSP, Communicating Sequential Processes approach. And the Lava framework uses it, and the main entity is process here, and these processes tend to communicate with each other, and it looks more brain-like than matrix multiplications. So again, it's interesting field. It's at its beginning. It's a good time to join and dive into it and to contribute and to develop your own algorithms and so on. You can shape the future right now just to start using something of these solutions. Pretty exciting time. It's hard to compare this framework to common deep learning framework, but anyway, Intel tries to do it. Of course, Lava has some exciting features that absent in other frameworks. That's not the main point. My main point is that Lava is interesting and worth spending time if you are interested in brain-like calculations. Let's skip this part for now. China developed their own chip. Maybe a few years ago, there was an article in Nature about their special chip, actually hybrid chip, half neuromorphic, half kind of common chip. Again, they have some number of neurons. They develop system that drive, I don't remember, bicycle or motorbike, something like this. It's, again, an interesting story. A lot of research happening here. Actually, in Russia, there are also some research in these directions, and some brain-like chips are developing, or at least were developed. An interesting chip is Akida, by Akida company. It's kind of affordable. It looks like you even can buy it. For Loihi and True North, it's pretty hard to obtain these chips. Maybe if you have links to IBM or Intel, you might, but I don't know anyone who has access to it. Akida looks like you can buy, or at least pre-order them and use in your own research. And I like this slide from Akida presentation. Again, it's very hard to compare these artificial neurons with real neurons, because the real neurons is still much more complex than artificial one, even this brain-like, kind of brain-like one. The biology neuron is a computer on itself, and neurons inside these processes, it's still much more simpler. But again, it's more complex than the matrix multiplications and the very simple neuron in deep learning. So again, it's a good movement, a good transition. And according to these numbers, Akida chip has more than 1 million neurons and 10 billion synapses. That's pretty decent amount. And comparing to some living organisms, somewhere between insects and small mammals like mouse or rat. So interesting, and we'll definitely see more such solutions. And these solutions can be joined into multi-processor configurations, and it's possible to develop something interesting and to contribute to research in this direction. Again, there are many different other approaches, many different other chips. Just 2 weeks ago, another article in Nature emerged. I put the link in the bottom of the slide. Again, it's very interesting architecture on its own. It's computing memory and based on some resistive random access elements. Again, a completely different architecture, completely different technology. Interesting to follow and to understand what's happening there. And this research is constantly emerging in different places, so keep an eye on it. There are many things happening there. So is it the whole story? Still not. Do we have anything else? Of course we have. I didn't mention memoristas. It's pretty popular in area of research, at least in some communities. Of course, there are quantum computing. It's a separate question on how is it applicable to deep learning, but again, it's interesting on its own. There are optical computers, DNA computing, and a very diverse and broad field of unconventional computing. If you haven't heard of it, just look at it, because it's very interesting. It includes almost everything from cellular automata to chemical computation to even living organisms like slime mold, that green thing. And this slime mold kind of able to solve different problems, maybe sometimes NP hard. So again, it's very interesting direction. Theory of computation is a great topic on its own, and unconventional computation is a separate, very interesting field on its own. There are many freaks actually, but a lot of interesting research happening there as well. So that's basically it. Some executive summary, I put it here. Just right now you have a pretty big range of solutions you can use. CPUs, GPUs, ASICs, FPGA if you want. Edge AI is a reality for a long time already. Almost any your phone or device use some kind of AI acceleration hardware. And neuromorphic is just on the rise. You cannot use it right now mostly, but there are many things happening there. So that's a good and interesting field. So that's it. And actually, a small bonus, completely irrelevant to the hardware, but I started to write a book on JAX. JAX is a great framework from Google. It could replace TensorFlow or PyTorch. It's really interesting. It's kind of NumPy with AutoDiff. Google XLA compilation to TPU, GPU, and so on. So I urge you to at least look at it, because some recent great research was done with JAX. DeepMind switched to JAX internally. Google does a lot of new research with JAX. So look at this library, it's interesting. Read this book as I write it. So it's a MIP, main and early access program. So chapters become available as I publish them. And actually, I have several codes to get free books. So I'll give you the 3 best questions to this talk. So feel free to ask questions. Thank you.
Thank you. Now questions for, yes, please.
Thank you for your awesome presentation. My first question is, what hardware architecture, what chips are more appropriate for 3D learning, deep learning, for example, in life sciences? And the second question is, what AI chips are used in quantum computing for the research, for example, in IBM Quantum, in DeepMind, in Rigetti Computing, and so on?
Could you please explain a bit deeper the first part about biology?
Well, it's 3D. Deep learning is somewhat different from 2D.
Yeah.
But I would like to start with 2D and then transfer to 3D.
Do you mean calculations on some grids of?
Yes, for example, the volume of proteins and so on. So it's difficult things.
Actually, I think modern GPUs and TPUs are pretty well for such things, because in many cases you use some convolutions for processing 3D structures. So that's a good choice. Actually, another thing is graph neural networks that emerge and are heavily used for protein folding, for some 3D structures as well. For graph neural networks, that's interesting. I believe that something like graph core IPUs or Cerebras could be a better choice if you can program them, but I think it requires additional experiments, and but it's an interesting field on its own. So I think right now there are no blockers to use deep learning on 3D data, on different 3D data. Maybe we'll see some even more advanced and more specialized architectures, but existing ones are pretty good as well, I think. And regarding quantum computer, I'm not an expert in quantum technologies, so I could make mistakes here, but I do not see a big intersection of deep learning and quantum computing right now, because quantum processes are pretty separate thing. Deep learning and AI processes is another thing. Actually, in quantum research, AI is heavily used, and even DeepMind produce a lot of research to optimize some quantum computations and so on. But right now, I think it's kind of decoupled from one another. So if you know some good example of how these things tend to converge, it would be interesting to know.
And one comment, please. When you talked about neuromorphic chips, but neuromorphic chips are also used. For example, they act as a human brain-like, and they are attached on the skin and wake on the 24/7 mode. Could wake on the 24/7 mode, giving online data for example, for biohackers. When they run and then sleep and so on.
Yeah,
are now used.
Yeah, I haven't heard of several projects that really use something like this. It's still not the mainstream, I think, but yeah, there are some movements, so it's great to see such non-traditional architectures being used for some real problems. So yeah, that's great. Thank you.
Other question? Yeah.
I have a dilettante question. So if you have a code which runs on Python on GPU, will it work if we change GPU to the TPU? I mean, seamlessly work on TPUs, or there will be some changes?
It's a good question. I think you can find a code that will not work, and some code will work. GPU has pretty different architecture, and in order to efficiently use it, you have to structure your code special way. Actually, Google has a separate section on their site on how to develop model how to write code to efficiently use TPUs. For example, TPUs are efficient on large batches, and for small batches it's pretty inefficient. So that's one example where your code could work, but the performance could be far from the peak performance, and even far from GPU. For example, I heard several times that people transfer their own code from GPU to TPU, and they see numbers that were pretty strange. GPU were faster. That's, I think, happens usually because you have to optimize for TPU, and it's worth spending time to understand the strong sides of TPUs and to restructure your computations and models in order to efficiently use it. But technically, I think in many cases it will work just by changing the underlying hardware. But again, there are caveats here.
Thank you.
Mm-hmm.
Another questions? Yeah.
You said that hardware is in golden age of AI right now. Imagine you are in your mid-20s. What can you advise in both spending like personal initiative, personal time to maybe invent something new, maybe do something in science, and both where to advance in terms of your skills, in terms of searching for a job, perhaps trying to like a new startup, something like this?
Yeah, that's a really good question. I try to look at things that I think could be very impactful in the future. I mentioned several of them. MLIR is one very interesting thing. I believe it will affect many things in a significant way, as LLVM affected a lot of compiler development and so on. So MLIR is important, and these things around compilation of different code to particular hardware is a huge topic on its own. It's worth investing your time if you are if you like these topics. Neuromorphic computing again is very interesting right now. I think it's very hard to find a job in this field, but maybe in 5 years it will change a lot. Right now, again, deep learning, I think, is for a long time with us, and you can just dive into current deep learning and track the changes, and it will be pretty kind of no-brainer just to be in the field and try some state-of-the-art approaches and be on the edge. The only important advice here is to constantly kind of relearn, because a lot of new research happening, and if you finished your learning in deep learning maybe a year ago, right now it could be a bit outdated because many different things emerged just in 1 year. So that's a field with a pretty fast pace. Actually, it's hard to recommend specific topics. I'd more recommend to be open to the world and to see what's happening, and to try to understand what could be impactful and what personally excites you. That's really important. If you start trying to follow the thing you are not excited, it's a bad choice. I can advise follow your heart here. It's really important.
Is there any evidence that neuromorphic chips could have better characteristics than the regular ones, like better generalization ability? Like, are they like regular ones, but they don't use as much power and they're somewhat worse? Or maybe they have better characteristics for some kinds of tasks, like reinforcement learning? Seems like a very natural choice.
Regarding generalization, I do not know any particular research that strictly says that neuromorphic hardware provides some better option. I think on the deepest level, on universality of computations, that almost any architecture can be used for anything. But yeah, neuromorphic have some special kind of biases that will help in particular problems. Right now, I do not see any particular large problem that will be solved with neuromorphic and cannot be solved with current hardware. Right now, I think the main selling point is energy efficiency, and again, it's still more research than production field, so it's there are no really large-scale models on which you can understand bounds of generalizations or something like this. So it's still an open question. But I believe we'll see some applications that will perform much better on neuromorphic hardware.
My question is regarding the JAX framework.
Mhm.
If there is no access to TPUs,
To what? To GPUs. Yeah.
Is there any motivation to think of switching PyTorch to JAX?
Yeah, JAX can still use GPUs as well. So,
but is there any additional improvements upon PyTorch code base?
Yes,
Switch to JAX?
yes, especially if you like functional programming. So JAX built around functional paradigm. It's pretty interesting on its own. And JAX is highly modular. And if you look at JAX ecosystem, it's blooming right now. There are a lot of different modules. And one really important thing is JAX not a deep learning framework. JAX is much more general. There are a lot of research where JAX is applied to physical simulation, for ocean modeling, to astrophysics. It's hard to see such many cases for TensorFlow or PyTorch. There are some, but
My question was mainly regarding to just training neural networks. Does it provide any additional benefits?
No, I think no significant benefits, because almost any modern framework allows you to do many different things. It's mostly if you're kind of entrepreneurial, open-minded, to understand what can be done different. So JAX is pretty different. And if you like clear code, again, JAX could be useful here. No, actually, there is one thing when JAX can help. If you work on very special, not mainstream problems, when you need to access to different things in your model, for example, you want to access both, for example, gradients, and you want to train different weights of your model by different algorithms and so on. If you want very tuning on the very discrete way, JAX is a perfect choice, because in TensorFlow and PyTorch, many things are hidden inside the objects, and sometimes it's very hard to get to them. And that's the good point where JAX is very useful. And actually, that's highlighted by the modern research. Many new things like vision transformers, other models are built with JAX. I think mostly because it was pretty easier to build such things in JAX than in TensorFlow or PyTorch. So try, and maybe you like it.
Maybe last two questions. Yeah.
You said big companies have their own specialized chips. Do they design it only, or do they also fabricate it? And how hard is it for relatively smaller companies to own their own specialized chips?
I start with the last one. It's very expensive, and for startups, it's usually not affordable, unfortunately. And regarding design and producing chips, it depends on what exactly do you mean by producing, because most of chips are produced in TSMC, for example, and in this sense, almost no company produce their own chips. They just make a design and send it to fabric in Taiwan, and the chips are produced there. But actually, the chips were designed usually in these companies. Google designed their own chips, and many others designed their own chips. And many of these companies, I think, fabless, they do not have their own fabs to produce physical chips. And I think that's a pretty common point. To build a fabric for chip production, it's a super expensive. I think.
Let me give number like Amazon acquired Israel Saranova company for $1 billion to build our custom chips. That's the idea.
Yeah.
Okay, next questions.
Yeah, thank you. Thank you so much for this wonderful survey. wondering, could you please elaborate more on the objectives of the neuromorphic computing?
Mhm.
Because, from the neurosciences right now, we get a lot of new information on how the human neurons are specialized and have different amounts of
Mhm.
synapses and so on. Is this information somehow used in the models of neurons that are in the neural chips, or
Mhm.
do they share the same mathematical model, or if not, which one is the closest to
Mhm.
logical analogs?
In neuromorphic computing, the neural models is closer to biology than in ordinary deep learning. That's definitely the case. These neural models are usually pretty programmable, so you can change different things and implement your own very special neurons. Again, it depends on the chip, but the Lava framework, as I understand, allows you to program pretty complex neurons, and I don't know what are the limits there. I believe it's still far from biology, just because I believe that a single cell, living cell, not even neuron, just an ordinary living cell, is a very complex, and it can do a lot of different computations on its own. It's still hard to do in all this hardware. But the trend is definitely towards the biology and towards recent models. And actually, human brain projects heavily invest into this field. And there are many objectives of why should we develop this hardware. One of the objectives is to better understand the brain. So it's a process that in some point in the future converges, I think. So it's hard to answer this question in its completeness, but I think it goes there.
Okay, thank you. Thank you so much.
Last question.
Yeah, actually, yeah. So again, thank you very much for your talk. It was quite informative. My question is about JAX on the hardware, especially the inference part.
Mhm.
So it's not secret that the framework provides the interface to leverage the full power of the device. For example, the community loves PyTorch.
Mhm.
Trying that, and they when running on Intel CPUs use Convino, or using NVIDIA GPUs use TensorRT, etc.
Mhm.
So I haven't heard anything about JAX. Like if you train your model on JAX and leverage during the training on TPUs,
Mhm.
how's the trend is going when training JAX and you're doing the inference on Intel CPUs or like pretty popular ones, NVIDIA GPUs, and etc.
Yeah, good question.
We see like specialized hardware which is accessible in public clouds. You can buy it and build your own prime infrastructure with JAX inference hardware.
Right now, JAX is mostly focused on research, not production. For production cases, you have to convert your JAX model into something like TensorFlow or maybe in PyTorch ecosystem. And there are some converters, for example, JAX to TensorFlow. You can convert a model and deploy it there. And JAX right now does not cover that part of spectrum on what to do with your models and so on. But I believe it will cover soon, because I think PyTorch started this way as well. PyTorch was great for researchers, and there was a lack of deployment options and for some time. Right now, PyTorch is pretty great, and you can use it almost anywhere. I think the same will happen with JAX, especially when such large companies like DeepMind and even Google is behind the JAX and they heavily used it. So I believe the future is very bright.
Thank you, Grigory.
Thank you.
We have correct time,
So I promised 3 quotes for this book. Let me choose 3. That's yours one, yeah, and regarding JAX again, and yes, just come to me. I give you links and.